Alright, hey guys, what's going on? So today we're going to be talking about spontaneous mass generation. In the last video we talked about spontaneous symmetry breaking. Spontaneous symmetry breaking, again, was a consequence of a loss of spontaneous symmetry breaking, again, was a consequence of what it meant to go from a mass term to negative mass square terms. When we're talking about spontaneous mass generation, we're going to be talking more about interaction terms and exactly how mass comes about when we consider interactions between fields. So let's get right into it. All right, so we're talking about spontaneous mass generation. And what we're going to do is we're going to take the following interaction Lagrangian. We're just going to consider the Yukawa interaction term. And it looks something like this. Okay, so now we want to make a shift in our Lagrangian. Similar to what we did last time, we're making a constant shift in our Lagrangian. So this is a constant. For all intents and purposes, this could be a constant. But what we're going to do is this is a constant that we came up with last time when we talked about our spontaneous symmetry breaking, right? So when we went from a potential to a new potential that defined that had an opposite mass term in it, a mass squared term in it. We found out that there was two minima, and so what that meant essentially was that our state could be in two ground states, the positive or the negative of one of those two minima. So we're going to shift our field by a factor of one of those minima, right? Again, this is really just a constant. We could do this for any constant, and we'll see that, again, it's really just an arbitrary constant when we're talking about shifting this Yukawa interaction, because, and here's why, right? So we plug the shift in, and then we get this. This guy right here is the same exact thing as we've seen here, but we have this new term right here. So we recover the interaction term, but now a mass term is added that is proportional to the coupling constant, G, and this guy right here. So this is kind of interesting, right? We know this is a mass term, right? Because in our Dirac equation, the mass term looked like this, right? So this mass term is it looks, when we're looking at this, is really this times this, right? So, or this mass squared term is really this times this. This implies that mass sort of spontaneously emerges once we, if we make a shift, right? And this shift, again, is a consequence of just shifting by a constant. So this implies that the mass sort of spontaneously emerges out of interactions, because making arbitrary shifts shows that there is a mass term in our Lagrangian. And so, what exactly does this mean? How can we? Well, I sort of talked about exactly what this means. How can we understand this pictorially speaking, right? So we have two fields, a scalar field and a spinor field, and there's an interaction between the two fields, right? So I've described that here, right? So this black part is the interaction between the two fields, and upon this interaction, we then get a mass, right? This is where mass comes from. And as we know in the last video, when we get mass, there's a loss of symmetry. So this is kind of, we're connecting things a little bit, right? With an interaction comes mass, and with mass comes a loss of symmetry. So if we put this into our spectrum picture that I've put in, that I talked about last time, on the positive ends where mass squared is greater than 0, then we have no symmetry. Where the mass squared is less than 0, we have no symmetry. We've talked about this. And when there is, when the mass squared is 0, then there is symmetry in our Lagrangian, right? We can see here that there's interactions when the mass is on both extremes, but there's no interaction or there's no interaction when our mass equals 0. And we sort of analogously said that there is this evolution from low to high entropy, and this, on a quantum mechanical level, can explain a lot of things, right? Because the low entropy is associated with symmetry, and high entropy is associated with less symmetry, then the one of the laws of thermodynamics, the idea that entropy is always increasing, that what that means is that the symmetry is always decreasing, right? In some very real sense, when things cool down, symmetry decreases, right? Things, if you have, say, a bunch of water molecules, they're bouncing around a liquid. You rotate that system, the liquids, the water molecules, really, it doesn't really look like the system has changed that much. But then when you cool it down a lot, then the water molecules will freeze, they'll turn into ice, right? So if you rotate the ice, then that system, upon that rotation, actually looks different, right? The configuration looks different when you rotate your frame of reference. And so that cooling down process implies there's a loss of symmetry. This is a very interesting way of looking at things. And it's, again, something that comes out of our quantum field theories, right? The field theories where the Lagrangian is sort of the name of the game. And that is spontaneous mass generation. So we've talked about spontaneous mass symmetry. Now we've talked about spontaneous mass generation. The next thing we're going to be talking about, and we're going to spend a couple of videos on this, is the path integral formulation of quantum mechanics and the path integral formulation of quantum field theory. Right? We're talking about quantum field theory, so I'm going to sort of be hinting toward, we're going to sort of talk about quantum mechanics first, and then in the next video following that is going to be a path integral formulation of quantum field theories, not as opposed to quantum mechanics. And so, with that being said, if you like this kind of content, please make sure to hit that like and subscribe button, and I will see you guys in the next video.